Alright, today we're talking about Riemann sums, which is really the start of our area under the curve focus. And, you know, for a long time that was a really puzzling question to mathematicians, was how do we find the exact value of the area underneath a curve? You know, they figured out how to find the area of a circle, which is something, you know, definitely non-trivial in its own right. And then, you know, over time they tried to extend that to other curves, ellipses, and then once we started graphing on an xy plane, you know, something like the area under y equals x squared. That would be an interesting thing to try to find. Okay, so the one on the left is actually it's probably something you could find in your free response packet. It's the type of thing that they would certainly have you calculate the area underneath. But if you look at it closely, since it's made up of line segments in a semicircle, we could use formulas from geometry to figure out that area. Okay, we know that we can figure out the area of a semicircle, we can figure out the area of these triangles, and we could actually find the exact value of the area under the curve. For polynomials like x squared, x to the third, sine x, cosine x, it's going to be a little more difficult. Okay. So we're going to start with the definition of a Riemann sum. A Riemann sum for the area under the graph of a continuous function on a closed interval is going to be given by the sum of a bunch of rectangles. Okay, and so we're going to pretty much say, okay, we're going to add up a bunch of these rectangles that have width delta x and height f of x. Okay, so we're going to add up a bunch of them, so each delta x is going to have its own value, and each f of x is going to depend on, you know, where along the sum we are. Okay, so it's going to be the sum over I of f of x sub I multiplied by delta x. Now, in general, the Riemann sums that we're going to add up, well, I guess except for the data in the table ones, the delta x is going to be constant. We're just going to say, you know, we're going to jump up a half each time, or jump up, you know, 1 unit each time. Or maybe they tell us to use 5 rectangles of equal width on an interval with length 10, and then delta x would be 2. But we have plenty of time to do that. All right, so here we've got some kind of continuous function that we're going to attempt to find the area under the curve for. And we're going to start with a left Riemann sum. And so you see we've divided up the interval from 0 to 8 into 8 sub-intervals. Now, to make this go a little faster, and to kind of prove a point I'm going to make in a little bit, I'm going to actually take each rectangle to have width 2. So we only have to add up 4, right? Because then we'd be adding up 8 rectangles, and that's kind of a lot. Okay, with a left Riemann sum, we are using left endpoints. Okay. So if our interval goes from 0 to 8, and we're going to divide it into 4 sub-intervals, okay, we're going to have these. And the endpoints that I'm going to use are going to be the left 4 endpoints. So it would be that one, and that one. And so what we're going to do is we're going to find that left endpoint. We're going to make a rectangle out of it. We're going to go to the next one. We're going to make a rectangle out of this one. It'll be all right. And then this one, okay, we're going to go over here. And the last one will be here. And then what we're going to be doing is we're going to be taking areas of rectangles by multiplying width by height. Okay, so this has width 2. Also, all 4 of these are going to have width 2. The height of the first one is 1. The height of the second one is 5. This one is 4. This one is 7. Okay, we can also take this data from the table, right? 1, 5, 4, 7. And so finding the area under the curve, okay, so the area is approximately equal to, we can tell that it's not going to be exactly equal to because, you know, we've got a lot of unaccounted for area over here. We've got some extra area on the second rectangle. It's going to be approximately equal to 2 times 1 plus 2 times 5 plus 2 times 4 plus 2 times 7. Okay. That is actually going to be a safe place to stop for us. But if you feel like you have to do the arithmetic, I would say, all right, I'll do 2 times 5. That looks easy. That's 10. I'll add 8, 18, 20, 34. So the area is approximately 34, using a left Riemann sum. Okay, for a right Riemann sum, we're going to do the same thing, except we are going to use right endpoints. So if I'm dividing into 2, 4, 6, and 8, well, I'm going to use these right endpoints. So we'll be ending up using these 4 values. That's what I'm expecting to see when I draw my rectangles. Okay, there we go, drawing a rectangle. Got another one here. Okay, they all have width 2 again. And then I can see from the table that the height is going to be 5, 4, 7, and 7.5. So I'll say that the area is approximately equal to 2 times 5 plus 2 times 4 plus 2 times 7 plus 2 times 7.5. It seems like that's going to be 10, 18, 18 and 14 is 32, and then 15 is going to be 47. Okay. I'm thinking that this one's definitely going to be an overestimate, but it's really tough to say on this graph because it changes from increasing to decreasing, it changes from concave down to concave up. It's really changing its behavior from along 0 to 8. So we won't be able to say confidently whether it's an overestimate or an underestimate. All right, for a midpoint Riemann sum, we're going to use the midpoint of each interval. And now, kind of when you're first starting, you're going to really like the midpoint Riemann sum. It seems ideal because it'll, kind of overestimate on one side, underestimate on the other. But they can be pretty unpleasant to calculate unless you have just a bunch of data. So I'm going to use midpoints. So for each subinterval, okay, the whole interval is 0 to 8. 0 to 2, 2 to 4, 4 to 6, and 4 to 8 are the subintervals. I'm going to use the midpoints. So that'll be 1, 3, 5, and 7. Then I'm going to use these, and I'm going to get a rectangle with height dictated by the midpoint of the interval. Is that right? I think this picture's a little off. And then I'm going to say, okay, that has height 4. This has height 4.5. Okay, oh, that's supposed to be 4.5. All right, well, maybe I can just put that in. Another 4.5, and this one's 8. So in this case, the area is approximately equal to 2 times 4, 2 times 4.5, 2 times 4.5, and 2 times 8. Okay, I've got 8 and 16 is 24, and then 2 9s is 24 plus 18, 42. And lastly, we're going to take trapezoid sums. And these can be a little annoying to calculate, but I've got something for y'all for this. Okay, use trapezoids. Now, I do probably need to remind you that the area of a trapezoid is we average the bases and multiply by the height. Okay, so is 1/2 base 1 plus base 2 multiplied by the height. Now, on these, when we just go to draw a trapezoid, it's going to end up being kind of a trapezoid turned on its side. So the height is actually delta x in this case. And see, this is a much more accurate sum. This is going to be by far the most accurate of the 4 sums we've taken thus far. But it is going to require us to use all of these pieces of data. 1 and 5, 5 and 4, 4 and 7, 7 and 7.5. All right, so in this case, area is going to be approximately equal to 1/2. Base 1 plus base 2 is 1 plus 5. Multiplied by the height is 2. Plus 1/2, you add up the 2 bases. The next one's going to be 5 and 4. Multiplied by the height, which is delta x. We're going to add in the third one. 1/2, add 4 and 7, multiplied by the height. And then lastly, the last 2 will be 7 and 7.5, and then we multiply by 2. And then anybody have a suggestion for what I should do here? Yes, cancel the 1/2 would be the thing to do if you felt like doing a bunch of arithmetic. I would recommend you stop and be happy with that. That is a number that represents the approximate area under the curve. It's equivalent to whatever you would get if you spent, 40 seconds typing that in the calculator, or, about the same amount of time trying to do the arithmetic. I would just recommend stopping, saying that's the area. And then if you really needed the numeric value, then you could go on and use a calculator or do arithmetic. But I'd say the trapezoid sum is one that's oftentimes best left in the long form. Okay, now we're going to talk about the exact value of the area under the curve, because that's why we're here. That's why we signed up for the course. Really, it's pretty fundamental to what we're doing. And anybody got a suggestion of how I could improve those Riemann sums? Those were not great approximations, but I could get a better Riemann sum by doing what? More rectangles. And that's how, some of y'all have discovered Math 9 on the calculator. Not really sure what you have needed it for besides physics. But if you discovered Math 9, you are having the calculator find areas under curves. And that's how the calculator does it. It does a Riemann sum, except with delta x equal to like 0.001 or something. And so really, as the rectangles get narrower and we get more of them, we get closer to the exact value of the area. So, okay, we're going to denote the exact value of the area with this integral, this definite integral. And the difference between the definite integral and the indefinite integral that we used last unit is the actual values of a and b right there. You see that? Okay, that's telling us to go from a to b. It's kind of the endpoints of where we're looking for area. And we're calling it a definite integral, and it's given by the limit of the Riemann sum. And if n is the number of rectangles, then we're going to want n to go to infinity, which will also necessitate that the width of each rectangle is going to 0. So I'll just put that there. It's the limit of the Riemann sum. So it's the limit as the sum I is going to run from the first rectangle up to the nth rectangle. It's f of x sub I multiplied by delta x. So, okay. And the reason why I want to, write the Riemann sum as the sum of f of xi times delta xi is that as n goes towards infinity, this is going to go to the integral, the sum becomes the integral of f of x dx. Okay. The f of x goes to f of x, the delta x becomes dx in the limit. And then we'll just put a to b so we know, where are we interested in the area of this function. Now we're going to talk about the quality of Riemann sums. And so much like when we said we drew the tangent line to a function and we analyzed the concavity to see if it was an overestimate or an underestimate, or we feel like there was another thing that we did this with. I can't remember. But this is where we're going to see, is our Riemann sum an overestimate or an underestimate? Okay, f is increasing. Now I'm going to draw two increasing functions. What's the difference between these two increasing functions? The concavity. So the point I'm making is that the concavity does not matter for left and right Riemann sums. Okay. So a left Riemann sum, I'm going to do in blue. A left Riemann sum is an underestimate. Over here, regardless of the concavity, the left Riemann sum will be an underestimate. With a right Riemann sum, if I start from the right endpoint, I'm just doing one subinterval, just for simplicity here. For a right Riemann sum, it will be an overestimate. When they ask you to give a reason for your answer, this picture is not good enough. What you have to say is that the left sum is an underestimate because the function is increasing. And it's very important that you not just, throw a bunch of stuff at the wall and see what sticks. Say it's increasing and concave up. If you mention the concavity when that's not relevant, that will actually invalidate your response because it's like, oh, maybe he doesn't know what he's talking about, if I were to say that. Okay, what else was I going to say? Oh, a trapezoid sum, we really can't tell, right? It would be tough to say. It could be an overestimate, it could be an underestimate. So we'll come back to that. F is decreasing. Okay, well, again, I'm going to draw the same picture. I'm going to draw a decreasing function that's concave down, or concave up, and a decreasing function that's concave down. I said it wrong. So first I'm going to do a left Riemann sum. And I'll do a right Riemann sum as well. So here. Right sum's an underestimate, left sum is an overestimate. Where the concavity comes in is when you're looking at a trapezoidal sum. So again, I'm going to draw the kind of a similar picture, concave up. I'll draw something that's smiling and increasing and smiling and decreasing. And then I'm going to come over here and I'm going to draw a trapezoidal sum. And we see that regardless of whether it's increasing or decreasing, the trapezoidal sum overestimates when the function is concave up. And when the function is concave down, so also said, we'll come through and we'll see that these trapezoids are underestimating. Okay, so, kind of a sample of what you would say is that the trapezoid sums overestimate the area under concave up functions. And we can say that a trapezoid Riemann sum underestimates the function when the function is concave down. So, for example, let's think about this. Think about this for a second, and then I'll ask y'all, is it going to be an overestimate or an underestimate? Okay, we're going to take the right Riemann sum approximation for the area under the graph of e to the x between 0 and 5. So what this really requires of you is to know about what does the graph of e to the x look like. Okay, well, here's 0. Maybe there's 5. We're interested in this area here that I'm going to shade. Do we think that this is going to be an overestimate with the right Riemann sum or an underestimate? Yes, it's going to be an overestimate. And what reason would we give? The function is increasing. Okay, so I strongly recommend to draw a one sub-interval Riemann sum. Okay, draw the rectangle. Okay, right Riemann sum overestimates. It'll overestimate the exact value of the area under e to the x between 0 and 5 because e to the x is increasing. And you can just say that e to the x is increasing. You don't have to prove that by taking the derivative and saying, well, e to the x is always going to be a positive number and e to the x is the derivative of e to the x, therefore it's increasing. You don't really need to do that. I think everyone would agree with you that e to the x is an increasing function. Here we got another good one. We've got a trapezoid approximation for the area under the graph of square root of x from 1 to 9. Okay, so again, you got to know what the graph of square root x looks like. I'll draw you a picture. Okay, looks like that. So I'll let y'all think about that for a second. Oh, I should probably mark off 1 and 9. What are we thinking on this one? Underestimate. What reason would you give? Concave down. You would not mention that it's increasing. It would not confuse the reader. It would sadden the reader, you know. And in terms of like the unit test, whenever that's going to be, that will certainly sadden this reader. You know, if you tell me that it's increasing, because I won't give you any credit for the reason. All right. So it's usually 1 point for the overestimate or underestimate, and 1 for the reason. But sometimes it's overestimate with reason, and that's really sad. If you get that it's an underestimate, and you don't get the reason part of it right, you get no point. And we don't like that. So here I am drawing a trapezoid. I can see that it's an underestimate, but that's not a good enough reason. So I write out a sentence, underestimate, because square root of x is concave down. All right, here we've got another good one, but I decided to change it a little bit to make it go faster. We're going to use a midpoint Riemann sum with 3 subintervals of equal length to estimate the value of the area under the graph of 4 to the x between 0 and 3. Okay, what I recommend doing is drawing a little number line just to make sure we're getting our interval right. Okay, so we're going from 0 to 3. There's 0. Here's 3. And we've got 3 subintervals, so, you know, it shouldn't be too hard to figure out what they're going to be. It's not always that easy. We're going to use a midpoint Riemann sum. So our actual spots that we're going to evaluate are going to be at 1/2, 1.5, and 2.5. So you could make a table of values also. You can make a bar graph. But either way, we're going to need to get some heights of these rectangles. Okay, so the height of the first rectangle is going to be, well, f of 1/2, if f of x is 4 to the x. Okay, so 4 to the 1/2 power. What is 4 to the 1/2 power? 2, because it's the square root. So that has height 2. Okay, next we're going to have to do 4 to the 3/2 power, and this figure is certainly not going to be drawn to scale. 4 to the 3/2 power, my recommendation in Algebra 2 and Pre-Cal to deal with rational exponents was always to deal with the denominator first. We know that the half power is the square root. So the square root of 4 is 2, and then we're still taking that to the third, which is 8. Okay, so that has a height of 8. And then 4 to the 5/2, again, take the square root first. We know the square root of 4, that's 2. 2 to the 5 equals 32. Oh yeah, this is really not going to be drawn to scale. It's on a logarithmic scale. And so we are going to actually approximate this integral. So the integral from 0 to 3 of 4 to the x dx is approximately equal to 1 times 2 plus 1 times 8 plus 1 times 32. So that's looking like 42. Okay, another one. Okay, we don't. I'm definitely going to sleep on this up today. Okay. F is a continuous function with f being positive, f prime being negative, and f double prime is not equal to, I bet that's supposed to say 0. Right, so the concavity is not switching. For all x on the interval 0 to 1, will a left Riemann sum be an overestimate or an underestimate for 0 to 1? For the area under the graph of f from 0 to 1. Now, I am going to pause for a second and draw your attention that f is positive. All of these things that I've said about overestimate, underestimate, with increasing, decreasing, concave up, concave down, is only valid if the function is positive. If the function dips below the x-axis, kind of all the bets are off. If it was uniformly negative, I believe that everything I said would be the opposite, but that is not going to happen on the problems that we're doing. We're not going to have to worry about that. We're going to have positive functions that we're taking the Riemann sum of, or if there was negative values, we would not be asking you about if it was an overestimate or an underestimate. Okay. So what are we thinking here? Anybody got any thoughts on a left Riemann sum for this function, or maybe how I should go about even attacking this? What do they always tell you to do in geometry? Draw a picture. Yes. Okay. I'm going to draw a picture of a positive function with a negative derivative and a non-zero second derivative. So I think that means you can just choose without any loss of generality, say that f double prime is always positive. So it's smiling. Why not? You know, it's Monday. Might as well be happy. And if f prime is negative, that means the function is decreasing. I don't know. Pencil's still in the back. Okay, so a left Riemann sum, you go over here and you just draw a left Riemann sum. Maybe you don't like the fact that I just used one subinterval and you want a couple of more and you want maybe a lot of rectangles. Either way, you can tell that this is going to be a what? An overestimate by the picture. Okay, be an overestimate because using the terminology they gave us in the statement of the problem, f prime of x is less than 0 on 0 to 1. Okay, that's something that I have not focused on in years past. Okay, saying it's decreasing is probably not going to be a problem. But ideally, you use what is given, or you justify because it's decreasing on 0 to 1 because the derivative is negative. And I'd really like to see that. That's a place where we can improve year on year. All right, now let's integrate using some geometry, find some exact values of areas under curves. That's pretty much what we're limited to today. We're not actually finding the area under x squared today, unfortunately. We're approximating it. Next time is the big reveal on how we're going to do that, although some of you are already aware of this. So, some integrals can be evaluated using formulas we already know. Well, how about let's just go ahead and integrate from 1 to 3. Well, this is f of x equals 2. 2 dx. Okay. Well, anybody got a suggestion for what they think that area is? Oh, I'm only going from 1 to 3. Yes. So, just draw the rectangle. Okay, yeah, this has width 2 and height 2. That's going to equal 4. That's an integral we can do. Over here, this looks like g of x equals 2 minus x. No, let's just make that 3 minus x and just say that it's kind of not drawn to scale, but that's 3 and this is 3. So the integral from 0 to 3 of 3 minus x dx is going to be equal to, well, it's a triangle, and I know how to find the area of a triangle. It's going to be 1/2 times the base times the height. So that's going to be 4.5. Okay, these are integrals that we can take right now. All right, why don't y'all try these on your own? Okay, this one we're going to be looking for this area. Okay, so the integral from -3 to -1 of h of x dx. And then over here, let's go from 0 to 2 on this one. Freeze the screen, see if you're doing it right. Okay, there you go.
Yeah, you can really hear those. Got some weight to them.
Okay, what are we seeing? Did anybody say that anybody get the wrong answer for the one on the right? Be off by a sign, and that would probably be the natural thing to do. You think area in geometry was always positive. Okay, in this course, the function being below the x-axis, we're going to need to reflect that with negative area for a whole lot of reasons that will become more obvious as we actually use integrals. But since f of 2 was -2, okay, if we add these rectangles, the sum of f of x times delta x, okay, f of x is negative. So the sum of f of x times delta x should be the sum of a bunch of negative numbers, which should be negative. Now we'll have plenty of more discussion on this as time goes on. All right, here we've got some more problems for us to do. And I think the point I'm trying to make here is that a function need not necessarily be continuous to be integrable. It does need to be piecewise continuous. So if I'd asked you about the integral from, say, 0 to 5, which that should definitely say 0 to 5. It says 0 to 7, but it should say 0 to 5. We can do that. There's no problem, okay? Because we'll just take the area from 0 to 2 and we'll add it to the area from 2 to 5. So as long as it's piecewise continuous, it will be integrable. Now, okay, the area from 0 to 2, I'm going to draw a little trapezoid. The height is 1, the other height is 4, the width is 2. So that's going to equal average the bases, multiply by the height. Okay, so that's 5. Yes. midpoint Riemann sums and trapezoids are really easy to calculate when the height is 2. It's ideal. Okay, the integral from 2 to 5. Bless you. I'm going to go over here, and maybe I'll do this in a slightly different color. Okay, this is going to be, it looks like a square, so it's going to have width 3 and height -3. So it's going to equal 3 times -3, which equals -9. So our total, I think oftentimes call it net signed area, is going to be, okay, well this is 5 and this is -9. Okay, so as we scan along the x-axis from 0 up to 5, well, I'll be adding 5 to -9. And that'll be -4. And this, I think, will be a good kind of segue into our integral properties. All right. I think the first one is the one that we were kind of up against on that previous example. That if we have the integral from a to b of f, and c is some number in between a and b, we can split up that integral into 2 sub-integrals and add them from c to b of f of x dx. There is going to be a constant multiple. Okay, so if we integrate some number times f of x, and we know what the integral of f of x is, know the area under f, well, it's just going to be k times as much area. Let's see, what else do we have? We have the integral from b to a of f of x with respect to x. Okay, now that's if we have kind of, an area here and we start counting area backwards, we're going to end up with the negative of if we'd counted it forwards. And again, that's another thing that we'll have more explanations on later, and it'll make more sense once we start integrating with context. But you can also think about it as delta x in this case. It's usually equal to b minus a divided by n, if we have a and b, divided by the number of rectangles that we're going to take. And if we go the opposite, then it would be a minus b, which would be a negative number. And delta x would be negative each time, and so you would end up with a negative of what you had before. Okay, so that's one way of thinking about it, but we'll have some more. All right, if we're adding 2 functions together and hoping to find the area under their sum, we can integrate them separately, know their sums, and add them together. Okay, next we've got another integral. And this one does not look obvious. But you know how to take this one. You have probably done this problem before at some point in your lives. Does anybody know what the graph of the square root of 100 minus x squared looks like? Yeah. And it was... Okay, so let's figure out what it's going to look like. I'm going to say y equals the square root of 100 minus x squared. Okay, well, we don't know what that is. So what can we do to both sides? Square it to just get rid of the square root, right? So y squared would equal 100 minus x squared. And do we see it now? Yes, it's part of a circle. Okay, and then we're going to add x squared to both sides, and we say x squared plus y squared equals 100. It's like, oh, yes, that's a circle, I think. Now, since y is the positive square root, it's going to be only the upper half of the circle. So it's the circle centered at the origin with radius 10. pretty easy. So mark that as 10, mark that as negative 10. You could even put that as 10, that y-intercept there. And if they want the area from negative 10 to 0, well, then that's going to be, oh, I know what I want. I want this. Yes, if I want this area, I've shaded it in gray, well, we know that's a quarter circle. So I could say that that integral is equal to 1/4 of pi r squared. So that's 10 squared is 100 divided by 4 is 25 pi. Okay, so that's one that we can do. And that is something that you could be expected to know, that the square root of a square number minus x squared is going to be a circle centered at the origin. All right, now that we did that good example, let's use our integral properties. Oh, I've got one that I didn't give y'all yet. What about this one in the middle? The integral from 7 to 7 of f of x dx. What do we think about that? 0. Yeah. Okay, the integral from 7 to 7 is at most like kind of a line that goes up from the x-axis to f of 7, but it's not even really. You know, it has no width. It's a rectangle with no width, therefore it has no area. Okay, well, if the integral from 0 to 5 of f of x equals 10, then what is the integral from 5 to 0 of f of x? Negative 10, yes. Okay, the integral from 0 to 7. Anybody have any thoughts on that one? It is, it's 13. Now I've got a better way for us to do this, though. I would recommend drawing a kind of a bar graph type picture, a really bad picture, or not even a bar graph, excuse me, just, you know, like here's f of x. And from 0 to 5, and from 5 to 7. And I'm just going to draw it as 10 and 3. Okay. So that would make 5 to 7 of negative 3 times f of x pretty easy. It's going to be negative 3 times 3 is negative 9. Now these up here, I'm going to just kind of show you this the once. If we did f of x plus 3, and I'll kind of color that in pink, I'll attempt to. Yeah, it's f of x plus 3. Really what's going to happen is there's going to be, it's going to be the same, except there's going to be a little rectangle with height 3. That didn't look good. Underneath. So it's going to be the integral from 0 to 5 of f plus the integral from 0 to 5 of 3. Now the integral from 0 to 5 is 10. And then 3 is, and if that's 5, that's going to be 15. So 10 plus 15 is 25. Okay, what I'm going to do is I'm going to find the integral from 5 to 7, but then I'm going to make it negative. Okay, so f of x minus 2 will be the negative of 5 to 7 of f minus the integral from 5 to 7 of 2. Okay, so 5 to 7 was 3 minus 2 times, okay, well, the integral from 5 to 7 of, oh, whoops, that's not right. 5 to 7 of 2, so that's going to be 2 times 2 is 4. Okay, so 3 minus 4 is negative 1, negative 1 is positive 1. Okay, here we've got f of x and g of x. So the integral from 2 to 6 of f plus g, so I'm going to split it into their respective areas. All right, and for this, my recommendation is that you draw another one of these kind of bad graphs. Okay. Here's f of x. 2 to 6, that was 10. And maybe g of x. Okay, I'm going to lose that second problem, but from 2 to 6. You can even, it doesn't really matter, just give you something to look at. Okay, 10 plus negative 2 equals 8. Then this one, g of x minus 2f of x. Okay, well that's going to equal the negative of the integral from 2 to 6 of And so g of x minus 2f of x would be negative 2 minus 2 times 10. And then we're going to make it negative. So negative 2 minus 20 more is negative 22. So I make that positive, and that'll be positive 22. All right, here we've got another one. We're saying that the integral from 0 to 5 of 3 times f of x is going to be 6. You know what, I'm just going to stop right there. And I'm going to say that that means that the actual integral from 0 to 5 of f of x is going to be 2. Okay, the integral from 0 to 5 of g is 7. And the integral from 3 to 5 of f minus g is 2. Interesting. All right, well, the integral from 0 to 5 of f of x minus g of x with respect to x is going to be, okay, so that's going to be 2 minus 7 is negative 5. Over here, 0 to 3, though, that's going to be a little more interesting. I think I need to draw a picture here. All right, I've decided I'm going to use the information I've already solved for and what we were given. It told me that the area from 3 to 5 under f minus g is 2. I determined that the area under f minus g from 0 to 5 was a total of negative 5. Okay, so basically 2 plus, maybe x is not the best, maybe it's like gamma or something. 2 plus gamma equals negative 5, meaning that this area gamma is going to have to be negative 7. So the integral from 0 to 3 of f minus g is negative 7. Okay, that was probably as difficult as these area properties are going to get.